So just quickly, definitions of shell elements. This is just a brief discussion. So when you start using software, you might be coming across these definitions: thick and thin shell elements, irrespective of whatever kind of software you are familiar with. So when you talk about thick shell elements, this actually follows Kirchhoff's plate bending theory. Okay, so in short, this Kirchhoff theory is ignoring the shear deformation in the shell elements. So each fiber, and this is the bending theory assumption. You also have seen this in theory of bending principles when you have studied strength of materials or structural analysis. So what it says is each fiber remains straight and normal to the mid surface plane. So here mid surface plane in case of shell surface, I mean shell element, is going to be the neutral axis. So if you just consider a fiber which is perpendicular to the neutral axis, this is going to be straight before and after bending, and it is also going to be perpendicular to the mid surface or the neutral axis. So this is what happens when you consider the thin shell element. And as I said, there will be no shear deformation in case of thin shell element, and normal stress orthogonal to the mid surface is ignored. So what it means, if you take a plate element like a slab or roof panel, and the normal stress perpendicular to the planned area is ignorable, means we generally ignore that because of the less intensity of that stress value. This happens because the thickness in the perpendicular direction to the plane surface is very negligible, and the plane area is considerably higher compared to the thickness. Then again, when you go to thick shell, it will follow the Mainline plate bending theory. This is actually considering the shear deformation also. So what happens because of shear deformation, you will see warping of fibers, means now the plane, if you consider a fiber or consider a plane perpendicular to the neutral axis, this is not going to be straight and normal to the mid surface. You will see some kind of warping or undulation on the surface. So this is an example of shell element with different degrees of freedoms assigned to it. Axis system you can consider as per your convenience. It may not be or it need not be same in all the cases or in your case. So now if I consider this axis system, and remember always according to your axis system, your degrees of freedom will change. Okay, so whatever I am showing here, don't consider this will be fixed or will be same all the time. It will vary depending on what axis system you are using. Now in this case, as you can see, my y-axis is in this direction, and this is x-axis, and z-axis is upward perpendicular to the plane surface. Okay, and this axis system is following right hand thumb rule. So if you are familiar with the right hand thumb rule, you will easily understand this. First you fix one axis and another two axis will automatically come. Okay, now I have fixed x axis here, and accordingly I got y axis and z axis according to right hand thumb rule. So now in case of shell element, you have total 5 degrees of freedom, compulsory 5 degrees of freedom at each node, and another optional degrees of freedom, which is rotation about this z-axis. This will give you a rigid body rotation. That's why we generally ignore that one. So if you ignore the rotation about z-axis, then you'll have these 5 degrees of freedom. So what are those 5 degrees of freedom? You have translation in x direction, which is ux, then translation in y direction, which is uy, then translation in z direction, which is uz. Then you'll have rotation about x-axis, and you'll have rotation about y-axis. These are the five compulsory degrees of freedom, and if you want to also consider the rotation about z-axis, you can consider, but that is not required for formulating any component in case of shell elements, because that will not make any changes in any of this, or any changes in any of the force components other than that rigid body rotation. Okay, now we'll try to understand in details each of these degrees of freedom and corresponding stress components what we get. Okay, we'll go one by one. So let us first start with ux. If you give any deformation along x direction, what will happen, and how the stress components will be generated and how it will look like. So first start with uy. I have started uy here first. So assume you have given a unit displacement in this direction, y direction. Okay, so because of either it can be in terms of displacement, or it can be in terms of force also. Instead of uy, you can say I have given force is equal to 1000 kilonewton in y direction. So both are same. It will give you the same stress components. So either you apply this uy or fy, you will get some stress generated in this surface with the direction shown with the green color arrows here. Okay, so this is basically in plane stress. If you see, uh, this plane is actually in plane with the axis of this shell element. So the sigma y is in plane stress in the y plane and in the y direction. So here I have written 2y, you can see, sorry. First y means the suffix. There are two suffix parameters. In this case, both are same, y and y. First suffix is representing the plane, which is y here, and second suffix is giving the direction, which is also y here. That's why in this case the stress components because of these forces or displacement in y direction will be sigma y. Okay, then let's say we are applying unit forces or unit displacement in x direction. So similarly, similar to y direction, in this case also normal stresses will be generated in the x plane and in x direction. So you will have denote this stress parameter using sigma xx. Okay, then let's say now this is not part of degrees of freedom, because the degrees of freedom will be orthogonal to each other, but because of the interaction between two degrees of freedom, you will get some extra stress components also. So this is one of that. If you apply some forces like that, which will have component in both x and y, so if you apply some forces like that, it will have component in this direction and component in this direction. Because of that, what will happen, you will have some shear stresses in both x and y plane. Now if you see, if you consider this shear stress, as I said, the first suffix parameter is indicating the plane. So this shear stress is in x plane, so that's why first suffix you see that is x. Then second suffix is the direction of action, which is in y direction. Similarly, because of the force which is acting along x direction but on y plane, so this will lead to the shear stresses in the y plane, which is shown by the y suffix here, and in x direction. So these are basically shear stress, as you can see, and these are again in plane shear stress. Okay, then next, this is the rotation we have applied about y axis. uh, if you could remember in the first slide what I have shown, that was xi xx something. So that was rotation. That's why we have represented that by xi. But here I am showing in terms of movement. That's why I have shown mxx. Okay. So if you apply either movement or rotation about y-axis, how the stress will generate. Now see, because of this movement or rotation, this plate will try to bend like this, so that the top surface gets the normal stresses, which is directing away from the plate, and bottom surface is getting the normal stress which is directing towards the plate. Okay, so this kind of stress will generate, and here I have shown just a portion of this surface, but don't consider this will be acting only in this much area. It will be acting throughout this plane. So entire of this surface, which is x surface here, entire of this x plane will be subjected to this kind of stresses. Okay, and this happens when you apply the rotation about y axis. So you get normal stresses in the x plane and along the x direction. Then next we have applied moment about x axis. Okay, but it will lead to the stresses in y plane and in y direction. That's why we will call this moment as myy, not mxx. If you see earlier, we have applied about y axis, but the name is mxs because it was acting in the x plane, and the stresses were directing also along the x direction. Similarly here we are applying the moment about x direction, sorry, about x axis, but it is causing the stresses in the y plane and in the y direction. Okay, again this whole y plane will be subjected to this kind of stresses, and here you see the top edge is subjected to the positive y stress and bottom edge is subjected to the negative y stress. So this moment will consider as a positive moment. How you will decide is, when you are applying a moment, the top surface which is along the positive z direction should be subjected to positive y-axis, sorry, positive, which is should be directed to the positive y, and the bottom which is along the negative z direction should be directed to the negative y. So like that you will decide the sign convention. Then also this is again not part of any degrees of freedom, but interaction between two degrees of freedom. Here if I apply moment in some random direction, so that it will have component in x and component in y. Okay, so like that we'll get some shear stress components also. So for example, suppose now I am applying moment not about either x or y, just in a particular plane. So this moment is not impacting the whole element, it is just impacting only this plane. For example, in this case, this is x plane, so I have applied this moment only to this x plane, not to the entire element. So this is like a torsion or twisting. With this moment I am trying to twist only this plane, not the entire element, in the sense of this whole element. So this is the difference between this moment and earlier when I applied moment about this x-axis. Okay, so if you try to twist only this plane, what will happen, it will try to generate some twisting stress also. In this case it is the shear stress. As you see, just try to visualize, you are trying to twist this, and because of that the top elements or top fibers above the neutral axis will generate the stresses in the positive y direction, and bottom fibers will generate the stresses in negative y direction. Similarly, if you apply some twisting in the y plane, not to the whole element, so again depending on the direction of movement, so now this movement, twisting movement, is directed with the arrow sign you can see here. So because of that, what will happen, again the top fibers will be uh, generating the stresses in this direction, and bottom fibers will be generating the stresses in negative x direction. And both of these stresses, this and this, are now not out of plane, this these are in plane again. Okay, so in plane means the arrow direction is not going away from the plane surface, it is within the plane surface only. In the first case it is still in the x plane, in the second case it is still in the y plane. So it is coinciding with the plane where the movement is acting. So that's why this will be in plane stresses, and both of these are shear stress again. So in the first case I have applied moment in x plane, but it was directing towards y direction, so it is mxy, and accordingly my stress is also denoted like that. Similarly in the second case, moment was in y plane, so first suffix is y and second is to the direction where it is acting, and accordingly the stress is denoted. Next, you might also have shear stress. So now this shear means this is the load acting along the z direction. Okay, so this we can denote either by q, p or something. So any alphabet you can use. So because of these forces, what will happen? For example, if forces is acting along the x plane, if I consider this as x plane, so because of that my x plane will be subjected to shear stresses, and these shear stresses will be directed towards the direction of the force. Okay, so this I have written in terms of tau xz, means the first suffix is indicating the plane where it is acting and second suffix is the direction where it is acting. Okay, similarly if you have some forces acting along the y plane and in the direction of z, because of that the shear stress what will be generated is tau yz. Again, first alphabet is showing the plane where it is acting and second one is showing the direction of action. Okay, next again another possibility, this is also tau yz. Now if you compare this tau yz with this, the stresses are similar but they are caused due to different phenomena. In the first case, these were generated because of normal forces. There is no movement, just forces is acting upward, which is generating the stresses. But in this case, there is not normal force. There is a movement. This is similar to, not similar exactly, same movement what we have seen here. Okay, torsional movement or twisting movement, whatever you say. So this torsional movement or twisting movement may also create stresses like this. Okay, earlier the stresses were in plane, means it was within the plane, not going away from the plane surface, but now it is out of plane. As you can see, it is directing towards down, so it will go away from the plane surface. Similarly, it is directing here in this portion, it is directing towards up, so it will go away from the plane surface. So this is because of this mxy. Similarly, because of myy, we'll see similar kind of stresses in y plane also. So now if you want to denote these stresses by some notation, so what kind of notations it will be? It will be similar to this, because in both the cases if you see the direction of forces are same, so their nature of these stresses are same, although they are created because of different phenomena. The direction can be either positive or negative, it doesn't matter, but you see the nature of the stresses in both cases it is same. Okay, so now let us try to understand different stresses in terms of, means with some example with respect to softwares. I have just taken example of ETABS. Similarly, whatever software you are using, you can always correlate with whatever is given in the software if you understand the principle. Okay, so we'll try to understand one by one. The first stress is sigma xs in plane. Okay, so if you go to ETAB, the parameter means when you are trying to provide some stiffness modifiers, people always get confusion which modifier will affect what, and to control a particular stress, what parameter should be modified. So there you may get confusion. That's why this is important to understand. So again, let us go back to sigma x, what it is showing, so that you'll understand properly. So this is sigma x. Okay, and according to the shell definition in ETABS, this is 2 direction. Okay, and this is 1 direction. Let me show with arrow. This is your 1 1 direction, means the y plane here is the 1 1 direction according to the shell definition in ETABS, and this plane where arrows are already acting stresses, this is 2 2 direction in case of ETABS. Okay, so according to that, if you want to control sigma xx in ETABS, so what you have to do is, sorry, this is F22 not F11 by mistake, this is S22. Similarly, F11, this is S11. Okay, fine. So I guess this is understood. Then again, sigma yy, this is in plane. So this is similar to this one, sigma xx. But here you have to control F11 to control this. And correspondingly stress you have to check S11. Then tau xy. If you could remember what was tau xy, this was tau xy in plane shear stress. So to control this in plane shear stress, you have to control F12 and you have to check corresponding S12 or S21 when you are checking the stresses from the analysis results. Then again you have sigma xx. Now it is out of plane, and let us again see what it is actually. This one, this is also sigma xx, but it is now because of out of plane bending action. Okay, so to control this, what you have to do again, you have to use this parameter m11 in ETAB stiffness modifier section, and correspondingly you have to check, sorry, this is again m22 not m11, m22, and this is s22, then this is m11, this is s11. So to control sigma xx because of bending action, you have to provide stiffness modifiers in M22, and when you want to check the stresses, you have to check S22. Similarly, to control sigma yy, you have to provide stiffness modifiers for M11, and correspondingly, when you are trying to check the stresses, you have to check S11. Then tau xy because of twisting, this one, sorry, not this one, this one, in plane shear stress. So this is similar to this one, tau xy. Although direction can be either positive or negative, but nature of stresses will be same. Okay, tau xy. So to control this, you can provide M12. So here you can see M12 and F12. The roles of these two parameters are going to be same because both of these will be controlling tau xy. But this is going to be because of the forces and this is going to be because of moments. And in both of these cases, if you want to check the stresses, you have to check the same stresses. Okay. Then tau xz. So let us see what is tau xz. This is tau xz because of twisting moments, and this is tau xz because of shear forces. So to control this, you have to provide these parameters, and correspondingly when you are checking the stresses from the analysis, you have to check S13, and similarly tau yz, this parameter you have to modify in the stiffness modifier section, and correspondingly you have to check the stresses S23. Okay, so I guess you have understood, and if you have some confusion still, it may take little time to understand, but at least if you understand the fundamentals you can go through once again, and definitely we can discuss whenever you have doubt regarding this. So now let us take some small examples to understand with respect to the results, so it will be more clear. Okay, so what I have done is I have taken just a shear wall simple shear wall subjected to some lateral loads, in plane lateral loads, and we'll try to determine the bending moment at the support portion from the internal stresses. Okay, and we'll try to relate this with the bending moment we get from the analysis. Okay, so the length of this shear wall, this length is 2 meter and height is 9 meter and thickness is 200 mm. So what I have done, I have modeled the same shear wall using shell element. The red color, here you can see this is shell element, and this one blue color is showing the frame element, means line element. Same shear wall I have modeled, once using shell, once using line element. Okay, to compare the result. So from the free body diagram, you can easily determine if 1000 kilonewton load is acting here, and if my height of the member is 9 meters, so definitely you can calculate the bending moment at the base will be 9000 kilonewton meter. So this is your externally applied moment. So now if you compare this externally applied moment with the internal moment, both should be same from the equilibrium point of view. Otherwise your equilibrium will not be satisfied. Okay, so that equilibrium we'll try to analyze now. Now see, I have taken the shell elements, and this is the stress contours after analysis and for a particular meshing size that I'll discuss later. I have checked the stresses at this point and at this point. Now first question is, there are so many stress components, which one to check for this particular case. Okay, so let us go to the software. Okay, so what I was talking about, if you want to check the stresses, analysis is completed, so you have to go to this option to check the stresses, and this is the load applied, and shell stresses you can select from this drop down, and here you have to select which component you want to check. Now my load is acting in this direction. Okay, so can you tell anyone which one to check, S11, S22, or S12, or S13, S23, according to whatever definition so far we have discussed?
S22.
Yeah, so we have to check S22 in this case, because as I said in ETABS, this plane is 1 axis and this plane is 2 axis. So if your lateral load is acting in this direction, your normal stress will be directing in this direction. So you have to check S22. Okay, now let us check S22, and here is the contour and check the values. Here you see it is 69. I think the value is visible, 69.36, and if you check here it is 69.35. So these two values I have taken, and here you see S22 69.36 and negative S22 is 69.35, and the variation is linear according to this. uh, I request you all to mute yourself, please. Okay, thank you. So the variation of this bending stress will be linear. Okay, now if you know this stress variation, you can definitely calculate the moment at this point. So that moment will be internal moment of resistance, and as I said earlier, this moment should be equal to the external moment if your analysis is correct. Okay, now here how you can analyze this one. So this is my stress at positive extreme fiber, and this is my stress at negative extreme fiber, and the shear wall length is 2 meters. So this is the plan view of the shear wall. Here you see the length and some thickness I have considered, which is not needed for the analysis, but height I didn't consider. And the thickness, this thickness I'm talking about, this thickness, this is 200 mm. So now if you interpret this stress with some variable x, how you can write the function. So this will be this one. You have positive extreme fiber stress and negative extreme fiber stress, and the variation is linear, and the length I have considered from minus L by 2 to plus L by 2. Okay, so here the limit you can see from positive L by 2 to negative L by 2, where L is 2000 mm. Okay, so if you simplify this one, you will get some function like that. Your S22 at any distance x from the center will be written as like this. Okay, so let us not discuss this one, because linear function you can easily find out this expression. Okay, now if I want to determine the moment with respect to this stress, so you know the definition of moment. Moment is equal to force into perpendicular distance. So force is again stress into cross sectional area. In this case, cross sectional area is this one. This plane is the cross sectional area, and the stress here I have shown with a just line, but again try to understand this whole plane will be subjected to this kind of stresses, but I have shown just one line. Okay, so you have stress, let us say constant stress S22 multiplied by this cross sectional area, which is T into L. Okay, so this is the cross sectional area, and multiplied by the perpendicular distance up to the center point, because I am now determining the moment about the center point. Okay, so this in terms of functions, how I can write this, let me open the slideshow. So I can write it like that. The limit is minus L by 2 to plus L by 2. Then I have stress function multiplied by the area. Now since I am taking the small fraction of area, because I have to integrate it. So this dA is representing the small fraction area multiplied by the perpendicular distance up to the center. So S22 into dA, it becomes the force, and this force multiplied by the distance becomes the moment. Now this is a small fractional moment, so this fractional moment should be integrated over the whole length, then only you'll get the total moment. Okay, so here I have just replaced this S22 function using the expression what we have just derived. Then this dA I can write T into dx, small fractional area. T is constant thickness and dx is variable, multiplied by the x, which is already there. Then T, since this is constant, I have taken it out from the integration, and I have multiplied this function inside parameters with this x. So the first parameter, first function multiplied by x plus second multiplied by x. So here also x, here also x, you'll get x square. So now this is simple things to integrate. You can all do this one. We have done the integration. So here you'll get x square by 2, and here you'll get x cube by 3. Okay, so if you now substitute the values of integration, you'll get something like that, and here you see this and this will get cancelled because this is positive and this is negative. So this will be over, and I'll have only this and this terms. So I just substitute the values of this S22 minus and S22 plus, and L is 2000, and if you do the summation for this, you will get this much. Okay, 9247.33 kilonewton meter, and I have obtained this for this mesh size, as you have seen when I was entering the mesh size 6 by 4. Okay, so what it indicates here is the result is dependent on the mesh. Whatever mesh you are using, it will definitely influence the result what we are getting. And in this case 6 by 4 mesh was not giving me the accurate result, because from the geometry and the free body diagram we have seen the correct result is 9000 kilonewton meter. Okay, so now see what mesh size will give us the appropriate result. So here I have written this comparison. In the first case, I have used the default meshing. So by default software do not mesh your element. So if I do so, I get the positive stress means extreme fiber stress 57.8 and negative 57.8. Okay. And if you do the calculation, you get moment of resistance 7706. So our correct result is 9000, but in comparison here you are getting 7706, so quite a lot different. Okay, so just try to visualize this one and relate with some kind of analysis what you have done in real case using shell elements, so you'll understand how much erroneous result can be if your mesh size is not appropriate. Okay, next see 2 by 2 mesh I have used, and these are the stress values I got, and accordingly my moment of resistance is this much, still different. Then I have increased mesh further 3 by 3, and these are the stresses, and this is little bit closer compared to 9000, and but still different. Then I have used 4 by 4, and these are the stresses, and now see it exceeded our values. So means this mesh is overestimating means going beyond the accuracy we want, so we do not want that much, so again we have to reduce the mesh. So what I have done now 3 by 4, and it was giving still higher than the result we expect. Then I have just altered, earlier it was horizontally 3 vertically 4, now I have done horizontally 4 vertically 3 elements, and in this case it was exactly 9000, which is what we expect it to be. Okay, then I have also analyzed what if I give a finer mesh. Sometimes people will have understanding that if I give smallest possible mesh size, maybe result will be accurate. So to check that one, I just 1 minute explore with higher mesh size. This is actually 10,000. So see, in horizontally I have used 16 elements, vertically 20 elements, and accordingly the result was 10,081 kilonewton. So this is again significantly higher than 9,000, which is the correct result. So here you can understand the thing. Uh, Lower mesh or higher mesh is not appropriate. There will be appropriate mesh size for your structure, and again the mesh size will vary from structure to structure depending on how complex your structure, depending on what kind of element you are trying to simulate. The mesh size, appropriate mesh size will vary. Okay, so in short, the significance what I want to put here is whenever you are using the shell elements, the result is always going to be mesh sensitive. So if you do not validate mesh size before proceeding with the analysis, your result may be erroneous, which is not acceptable in real. Okay, so that's why always try to validate the mesh size before using it in any practical purpose. Otherwise, sometimes what may happen, you have analyzed everything correctly, you have done the design correctly, but maybe structure failed when it is constructed because of this small error. Okay, so now let us see another example, just a random figure I have taken to explain the things. Don't go with the shape or what kind of structure is, leave it. Okay, so this is actually deck slab, let us say. with some random shapes, some random loading. As you can see, this is the slab, and consider this vertical member as pier below, and load is acting in the x direction as well as in y direction. These arrows are not showing upward direction, it is actually y direction. And there is also a uniformly distributed load of 25 kilonewton per meter square on the slab itself. So now let us put some questions here. So for this loading condition, let us consider we are trying to design this slab or deck slab, and our intention is to design the horizontal reinforcement in x direction and horizontal reinforcement in y direction, and also to design the shear, means to check the shear stresses. Okay, so now I have these questions, and you tell me which stress component or which modifier should be checked in this case. So first, let us say I have to design longitudinal reinforcement, or I have to check bending stress sigma xx according to the shell definition in ETABS. As I said already, this side is going to be your 1-1 plane, and this side is going to be your 2-2 plane. So can anyone tell me for this what stress I have to check from the output results? I mean here, which one should be checked for this case?
S22.
S22. See, this is my axis system. Okay, so consider this axis and tell me which stress component should be checked. Can I say it sigma 1-1? So I have to design longitudinal reinforcement along x, means the reinforcement direction is this one. So what will be the direction of stress? Will it be in the direction of x or in the direction of y? Stress direction I'm asking.
Z.
No, z will give you the shear stress. I am not
Sir,
talking about the shear
then sir,
stress.
Y, sir, Y horizontal.
Let me try something different. Maybe you'll understand. Let us consider a beam. This is a beam, and I have to design horizontal reinforcement now. Okay, so horizontal, if let us also put the axis. This is x, and this is y. So horizontal is x, vertical is y. I am not writing x, y. So now I have to design the longitudinal reinforcement along x. Okay, what stress I generally check for this? Is it x stress or y stress?
Y,
Y.
the flexural load.
Flexural load, that is fine. 1 minute. So
Stress will be like sigma xx in the direction of x it will come.
So this is movement, right? This is the movement we'll design for. Is it correct?
Yes.
So now
Yes.
this movement, what kind of stress it will cause in this member?
Compressive above the neutral axis and tensile below the neutral axis.
In the x
Yeah,
direction.
that's perfectly correct. But what will be the direction?
The tensile will be in the x direction and the compressive will be the negative x direction. Yeah.
Is it correct?
Yeah.
Yes.
So it means for designing the x direction reinforcement, you have to check the stress in x direction, right? Can I say that? Can I say that?
Yes.
So now tell me which stress I have to check here. I have to design the reinforcement along x. And the definition of shell, I think I have to write here it. If this is your shell element, this is your sigma 11 and this is your sigma 22. So here this horizontal is showing 1 axis according to the definition of shell in ETABS. Okay, and this is sigma 22. So now this is my x axis and I want to design the reinforcement along x axis. So from this definition, which stress component I have to check?
Sigma 11.
Sigma 1. That's correct. So similarly, I have to design the longitudinal reinforcement. Sorry, this is y. So I have to check bending stress YY. Which stress component I have to check?
Sigma 22.
And that's perfectly correct. Sigma 22 I have to check. Then I have to check the shear check in XZ plane. So this is the axis system. So you have XZ plane. So which stress component I have to check from here?
S12.
S12.
Yes.
Anyone else? Is it
S13.
S13? Then anyone else? Okay, so let us go back to our discussion again.
S23.
Okay, I got three answers. Let us see now. Okay, so again, this is the definition of shell and this is my axis system. Okay, this is 1 1, this is 2 2, and I want to check in 1 minute XZ plane. So XZ plane is going to be this plane. So this is my x direction and z is upward. So this plane I was talking about. And let us go back to our initial discussion. This is actually S12, the tau xy in plane. This is S12. So it cannot be the shear check. Okay, so this is not correct. S12 is not correct. Then this is also in plane tau xy. So same thing S12. This is also not correct. Then this is tau xz. Okay. Now, according to ETABS shell definition, is it one plane or two plane? This plane.
One.
No, it's two actually. Here you see, I have written this is two. So if this is two, this is also two, right? And this is one. Okay. So this is 2 plane. In this case, this is x plane. Okay, and z direction. So I have to check the stress. So it is going to be 2 3. Okay, if you see here, this is my x plane, which is this plane corresponding to this plane. So this is 2 plane actually, and the direction is z. So that means 3. So I have to check 2 3, not 1 2, not 1 3. Similarly, so let me write it. This is going to be S2 3. Similarly, what about this YZ plane?
1 3.
S13.
Yes, yes. So this is going to be S1 3. And in plane shear check, what about this?
1 2.
S1. Okay. So these are the things what actually people get confused when you are analyzing various kind of structures like bridge deck. You want to analyze a bridge deck and design the reinforcement, and there is a chance that you'll get confusion in interpreting the results. In case of bridge deck, you have to be careful about this because you are going to design reinforcement about x direction, you have to design the reinforcement about y direction, and you have to check the transverse shear also, these two. Okay, in plane generally we ignore either it is bridge or any kind of structure because in plane rigidity is much higher. So this you have to understand which direction which component should be checked. Okay, if you understand this one, definitely your analysis is going to be reliable, otherwise you have to be careful. Okay, I think things are a little bit clear now, and as I told, this was a short discussion. So definitely if you have any more doubts, if it is answerable here, I'll try to answer, otherwise we can have in a future session. So in the
Tajal, I have just one general doubt. Like,
yes.
generally we have a 3D solid element.
Mhm,
Now, if we want to idealize into a thin shell or a thick shell,
mhm.
and then what are the degrees of freedom we have to consider? So, is there any guideline document for that?
Yeah, definitely. You have no, I didn't get your question properly. You have solid element and you want to model the solid element using shell element.
Yeah.
Yeah, so you have to understand what are the degrees of freedom in solid element and what are the degrees of freedom in shell element. And if you understand those degrees of freedom, you can interpret the result easily. Okay, so now in shell element, as we have discussed, these are the degrees of freedom. You have 5 degrees of freedom in case of shell element, but in case of solid element, you will have only first 3 degrees of freedom, only translational, no rotational degrees of freedom in case of solid. Okay, so in this case, if suppose this is the solid element, so you'll have only 3 degrees of freedom at each node, which are going to be translation in x, translation in y, and translation in z. So now suppose you want to determine the stress. How to determine the stress? What you have to do, you have to determine the displacement at two nodes. Then you have to differentiate the displacement. So you'll get the variation means strain. Then you have to convert that strain into stress. Indirectly you have to determine the stress. Okay, so that is going to be the procedure in solid element. But same solid element, if you model using shell, so you don't have to convert the displacement into stresses. You can directly read the stresses because it is giving you stress. These parameters will give you the stresses. Okay,
Okay.
okay, next, any more questions?
Sir, regarding the fixity, like sir,
Yes.
we know that no any structural element is 100% fixed at their ends.
Hmm.
So, sir, we will not get the correct bending moment or the shear force exactly. So, sir, what property modifiers we like in the case of the shear wall that we designed right now, sir,
Hmm.
uh, that is fixed at the base. So, we're getting at 9,000 moment from the equilibrium condition, but
Hmm.
that will be not the case in the practical situation. So, sir, how to like assign the degree of freedom to the fixed joints? Sorry, how to assign how much degree of fixity is there at the fixed joints?
Okay. So this question, see, it answer is not a means common answer. It depends on how much understanding you have about the condition at the
Yes, sir.
connection point. Suppose you know what kind of interaction is present at the connection. For example, if this shear wall is situated or lying above a mat which is very
Yes, sir.
large area and thick, so definitely their rigidity will be much higher compared to if when it is lying just
Uh-huh.
above the soil.
Yes, sir.
Okay,
Yes.
so it depends on how much understanding you have. And in case of soil, definitely suppose you are trying to construct a shear wall directly on the soil,
Yes, sir.
so definitely you have to determine what is the stiffness of soil beneath the shear wall. There is no other option. But
Sir, can we design like assuming there is a spring and after that analyzing how much stiffness is, how much stiffness of the spring is coming after that assigning the property?
yeah, that's what I'm saying. If you want to model a spring below this shear wall,
Yes,
then
sir.
you have to assign the spring stiffness, and that you have to decide based on the testing on soil. Okay,
Yes, yes.
so it cannot be predefined. There will be no predefined value. You have to identify that value and you have to assign it to your model.
Mm.
But normally what we do when we design the means analyze the building models, we generally fix the support at the base. Okay, because we take entire area of soil which is very much large compared to the building, and in case of hard soil generally the stiffness is very much higher, so it is reasonable to consider fixed support. Okay, but
Yes,
suppose you
sir.
have soft soil, so if you provide the fixed support there, it will not be accurate. You have to determine the strength stiffness of soil, then you have to model the soil as a spring below the foundation, sorry, below the columns, then there you can provide the stiffness.
And sir, what about beam, a beam and beam joining to another beam, like primary beams are joining to the secondary beams?
I got it. Now let's say I have one beam connected to between these 2 points. Okay, so your question is how much fixity should be provided here, right? It's not called fixity, it's called joint rigidity. Okay, so based on some testing and verification, people have identified because the concrete joints, it acts like a rigid joint, but there is no full rigidity because joint is subjected to extreme stresses, so there is a chances of cracking. Okay, so considering all those factors, they have decided if we provide 50% rigidity, means
Yes, sir.
the full rigidity of the section that divided by 2, so that much rigidity if you provide, it is reasonable. So this can be provided by going to the joint offset. You go to joint,
Yes.
then there is a option of joint offset. Yeah, rigid zone factor, there you can provide 0.5 and okay. So now this joint will be considered as 50% rigid, not fully 100% rigid. Okay, so like this you can model beam column joints in RC building analysis.
Thank you, sir.
Okay, okay, do we have any more questions? Otherwise we can close this session. And if you have further questions, definitely you can raise in our WhatsApp group. We'll try to clarify. Thank you everyone for attending this session, and hope to see you soon with another session.
Thank you. Thank you for the informative session.
Yeah. Thank you. Thank you.
Thank you.